So this is the Waves homework booklet question 23. A couple of multiple choice questions. Starts with monochromatic light passing from air into water. Which of the statements is true? It's all about whether or not the velocity, the frequency, the wavelength change. Starting point, we could start thinking about this through definition of refractive index, is that the speed will change. We've got a refractive index different in air and water, therefore I'm going to have a different speed. Obviously the speed in a vacuum stays the same, so with the refractive index being the speed in a vacuum divided by the speed in the substance, we know we've got different refractive indexes for air and water, therefore I must have different speeds in the substances. So the velocities definitely are different. We've then got to think about c equals f lambda. Now that means that if I've got different speeds, what about the frequencies? What about the wavelengths? Well, the frequency can't change. If you have frequencies changing at a boundary, that means you're either creating extra waves at that boundary or waves are disappearing at that boundary. So the frequency can't change. If the frequency is fixed and the speed is changing, therefore the wavelength must be changing as well. And that leads us to C, the velocity and wavelength change, but not the frequency. Just check the others. Velocity, frequency and wavelength all change? No, because the frequency can't. Velocity and frequency change, but not the wavelength? No, because the frequency can't change. Again, the wavelength in fact has to. C, we've agreed, is right. And D, the frequency and wavelength change, but not the velocity. No, we know the velocity change because we've got different refractive indices, but different materials. 24, not a multiple choice question at all. Diffraction grating, 300 lines per millimetre, illuminated with monochromatic light of 540 nanometers. Calculate the order of the second order maximum, giving your answer to the appropriate number of significant figures. First thing with these, we're obviously going to use wrong button. We're going to use n lambda is d sine theta. First thing we're going to want to deal with is to calculate what d. We've got 300 lines per millimetre, so the distance from one to another is that 1 millimetre divided by the 300 lines I've got in each millimetre. That gives me 3.33 times 10 to the minus 6 metres. Then it's straightforwardly lobbing it into the equation. N's 2, there's the wavelength. I've got to get my power of 10 right. Nano, 10 to the minus 9. D calculated sine theta. I can work out that sine theta is 0.324. Then use sine minus 1 on my calculator to work out that gives me an angle of 18.9 degrees. Giving your answer to an appropriate number of significant figures. They wanted 2 or 3. I think I would argue that that's 3. I think I would argue that that's either 2 or 3, so they were accepting that that was 2 or 3 significant figures, and that was questions 23 and 24 from the Waves homework booklet.